Hi everyone, today our lecture is Work and Energy Part 2. Hello everyone, this lecture is Work and Energy Part 2. In this lecture, I will identify kinetic energy and work energy theorem. Let's start with Newton's second law. So sum of all forces equal to ma. Now, d work total, it's actually equal to integration F net dot delta R, and F net in this case equal to ma. Now in this one here equal to m, and a is the first derivative of the velocity with respect to time, so dv by dt delta R, and work total in this case equal to integration m dv. Now delta R delta t is actually v, from v1 to v2, or we can say that work total equal to half m v square from v1 to v2, or work total equal to half m v final square, or v2 square, minus half m v initial square. Now half m v final is the final kinetic energy, and half m v initial, it's the initial kinetic energy. In this case here, work total equal to delta K, and this one here it's called work energy theorem. So here work energy theorem. And by the way, this is the most important equation we have got so far. Back to work total equal to delta K. Now work total is the total work from all forces in the system. Now all forces in the system, sometimes we have external force applied on the system, and sometimes we have frictional force, sometimes we have gravitational force, and sometimes we have spring. In this case here, work total equal to work from external F plus work from frictional force plus work from gravity plus work from spring equal to delta K. That's the meaning of work total. Now we look at the system and see, do we have spring or gravity or friction or external force? And the work done by all forces in the system equal to delta K. Now let's have this example. Now 3 balls of equal mass start from rest and roll down different ramps, as we can see in this one here. All ramps have the same height. So the height for all ramps here is the same. This is 1, this is 2, and this is 3. Which ball has greater speed at the bottom of its ramps? We need to calculate the speed of the ball right at the bottom here. Now let's see. In this case here, if we take work total equal to delta K, in other words, work total equal to half m v final square minus half m v initial square. Since the all balls start from rest, this one here is equal to 0. Now work total, as we mentioned before, we have 4 different cases: spring, gravity, external force, and friction. Now, we have no spring, and we have no friction, and we have no external force. The only force we have here is gravitational force. In this case, the work total here, it's actually only work done by gravity, which equal to half v final square, or mgh equal to half v final square, mass with mass here, or v final equal to square root of 2gh. This equation here means that the final velocity depends only on the ramp height, which means all balls will have the same speed right at the bottom of the ramp. So the answer is all balls have the same speed at the bottom of its ramp. In this example, a truck initially at rest rolls down a frictionless hill and attains a speed of 20 meters per second right at the bottom. To achieve a speed of 40 meters per second at the bottom, how many times higher must the hill be? To answer this example, let's go back to the results we obtained in the previous one, this one here. So v final equal to square root of 2gh, or we can say this v final square equal to 2gh. Now in the first step, the speed of the truck right at the bottom is 20 meters per second. So if we substitute 20 back in here, we'll get 400 equal to 2gh. H in this case equal to 400 over 20. In other words, it's equal to 20 meters. Now, in the second case, when the speed at the bottom equal to 40 meters per second, in this case 1600 equal to 2gh, h in this case equal to 1600 divided by 20, or it's equal to 80 meters. Now, as we can see here, when the speed is 20 meters, the height is 20 meters. Now, when we doubled the speed to 40, the height is 4 times the initial height. So, h2 is actually equal to 4 times h1. Because the relation between the height and velocity is this: h is proportional with square of v. Example. In this example, Mary and Adam start from rest at the same time on frictionless water slides with different shapes, as we can see here. At the bottom, whose velocity is greater? Now, in this case here, this is Adam here and this is Mary. Both start from rest in different tracks and different shapes. Both start from the same point and both end at the same point, in this case here. Now, which one will have greater velocity right at the bottom of this tracks? Now, work total in this case here equal to delta K. Now, we have no friction, we have no external force, we have no spring, only gravity. So work from gravity equal to mgh equal to, since they are start from rest, we only have the final kinetic energy here. It's equal to half v final square. In other words, v final square equal to 2gh. This very important result here indicates that we are really interested in the initial and the final positions of the track. We are not interested in the track itself, so only the initial and final positions of the track. So to answer this question, both Mary and Adam will have the same speed right at the bottom of this track. It doesn't matter the track shape or how long the track will be, as long as they both start from point and end up with the same point. Now, as the second part of this question, who makes it to the bottom first? Now, even though they both have the same speed at the bottom, as we can see here, Mary will have lower height than Adam for most of her ride. In this case, Mary will reach the bottom before Adam. So to answer this, Mary will reach the bottom first because she has lower height than Adam. In this model, we can see here a cart placed on a frictionless ramp with height h, this one here. Now, as we can see here, the cart has potential energy equal to 4.76. No kinetic energy whatsoever. Now, when we start the model, we only have two forces here, the gravitational force and the normal force. In this case, the kinetic energy start to increase and the gravitational potential start to decrease. In the graph here, we can see here the gravitational potential energy start to decreasing here, and the kinetic energy here start to increasing. As we can see here, now all the gravitational potential here will be transferred to kinetic energy right at the bottom of the ramp. So in this case, we are interested actually in the initial position of the cart and the final position of the cart. In this model, we have here three different balls. The red one with mass 0.1 kilogram, the blue one will have mass 1 kilogram, and the green one will have a mass 5 kilogram. We drop all the balls from the same height, this one here. Now, the potential energy, as we mentioned before, it's equal to mgh. So U here equal to mgh. So the potential energy depends on the height itself and on the mass. Since they all have the same height, the only crucial parameter here is the mass of the object. Now let's see, the potential energy in this case is the maximum this one here. So let's start the simulation and see here. Now the potential energy, let's see here. The green one for the green ball here starts from maximum value because it has a maximum mass, and then the blue one, and then the red one. On the other hand, the kinetic energy starts from 0, this is green one, and the blue and the red start from 0 and start to grow, while these balls start to decreasing the potential energy. Let's see here. Look at the curve here. The potential energy curve is the opposite of the kinetic energy curve. Increasing the kinetic energy will decrease the potential energy and vice versa. Get the curves here. In either case, mass plays a crucial role in the value of the potential energy and in the kinetic energy, as long as they all have the same height. As another model, we dropped a ball with mass 1 kilogram and displacement in the y-axis here, it's equal to 1 meters. Starting from this position here, we only have gravitational potential energy, which equal to 10 joules. Now the kinetic energy here, it's equal to 0. No friction, no air resistance whatsoever. In this case, if we start the simulation here, now the potential energy start to decrease and the kinetic energy start to increase. If we add the kinetic energy and the gravitational potential energy together, they must equal to 10 joules. While the potential energy decreasing, the kinetic energy increasing. Let's continue here. Now the maximum kinetic energy we obtained here is 10 joules, and the gravitational potential energy is equal to 0 in this case. All the potential energy turns into kinetic energy and vice versa. Similar to the previous model, we throw a ball vertically upward. As we can see here, the kinetic energy starts to decrease because it's going upward and the velocity is decreasing in the positive direction. On the other hand, the gravitational potential energy starts to increasing because the height of the ball is increasing. When it reaches the maximum height here, the kinetic energy will be 0 and the gravitational potential energy will be in its maximum value. Look at the curve here. The obtained curve for the kinetic energy here is the opposite in direction as the obtained potential energy curve. If we look at this graph here, the velocity of the object starts to decreasing until it reaches this point here, this one here, and then it starts to increasing in the negative direction. Now let's have an example. A cart starting from rest rolls down a hill, and at the bottom it has a speed 4 meters per second. Now the cart given an initial push, so its initial speed is 3 meters per second right at the top. What would be its speed at the bottom? Now let's sketch the situation. So we have here a ramp or a hill here, this one here, and here we have this cart. Now at the first stage it starts from rest. It means v initial equal to 0, so we only have here h in this one here. Now at the bottom the speed here it's equal to 4 meters per second. Now we will use this information to find the height of this ramp here or this hill here. So work total equal to delta K. Now the only force we have here is the gravitational force, so mgh equal to half m v final square minus half m v initial square. Now since it starts from rest, this one here is equal to 0. Now mass with mass, as we can see here, so h here it's equal to v final square divided by 2g, or h here equal to v final it's equal to 4 meters per second. 4 square divided by 2g, it's a 20, and in this case 16 over 20, which equal to 0.8 meters. Now let's back to the second case, when the cart here given an initial speed equal to 3 meters per second. We would like to find how much the speed right at the bottom. Now we will use the same rule here. Work total equal to delta K, in this case here. Now work total mgh equal to half m v final square minus half m v initial square. Now this one here isn't be 0 because we have an initial velocity equal to 3. Now h here, we just calculated h in this one here. Now mass with mass with mass here. Now 0.8 multiplied by 10 equal to half the final square minus half 3 square, it's 9. You solve this equation here, you will find the final equal to square root of 25 or 5 meters per second. Example: a box sliding on a frictionless flat surface runs into a fixed spring which compresses at distance x to stop the box. If the initial speed of the box is doubled, how much the spring compresses in this case? Let's sketch the situation. So we have here spring, and we have a box with initial velocity here. Now the box will compress the spring until it stops. So this is here after the compression. So this is the relaxed position for the spring, x equal to 0, and this is the final position of the spring, this is x final. If we double the speed of the box here, how much the spring will be compressed? Now before going through this example, let's have this model. Now in this model here, a cart is connected with a spring and is given an initial velocity here. As we can see here, the kinetic energy of the cart here start to decrease until it reaches the maximum elongation for the spring. Then it becomes almost zero. Let's just move a little bit and start to increase until it moves around the relaxation position. Then the kinetic energy start to decrease until it reaches to maximum compression, and so on. Now the elastic potential energy will work in the opposite way. When the spring will have maximum elongation and maximum compression, the kinetic energy will become zero, but the elastic potential energy will be maximum at the maximum compression and maximum elongation. At the relaxed position, the elastic potential energy will be zero and the kinetic energy will be maximum. Let's see here. So it oscillates around the relaxed position of the spring, around this one here, back and forth. And look at the elastic potential energy and kinetic energy of the system. Now back to our example here. Let's start with the most important equation, work total equal to delta K. Now the question is, 4 types of forces we might have in the situation. We don't have external force and no friction whatsoever in this case. Gravitational force is equal to 0 because it's an object here, it's in the ground, and the only work done here is the work done by the spring. Now work done by the spring equal to half the final square minus half the initial square. Now work done by the spring, it's equal to half kx initial square minus half kx final square equal to half the final square minus half the initial square. Now the initial speed for this case here, it's v. Now this one here, it's given. Now the final speed for this box is getting into 0 because the spring is compressed into maximum compression, so the final here equal to 0. Now the elastic potential energy of the spring when it's in a relaxed position, it's equal to 0, and the elastic potential energy of the spring when it's in maximum compression, it's equal to this one here. You just simplify the equation. Minus with minus goes out, and half with half, in this case kx square final equal to the initial square. Now from this equation here, as we can see here, the x final, the displacement here, is related with v itself. So x square is correlated with v square. In other words, x is related with v. Now if v is doubled, then x will be doubled. Now to answer this question, x will be doubled. Example, a 3 kilogram object slides down a 0.5 high ramp from rest at the top of the ramp. If the work done by the frictional force, this one here, on the object, it's equal to minus 5 joule, what is the speed of the object at the bottom? Before going through this example, let's have this model. Now in this model here, a cart here located at the top of the ramp, this one here, and starting from rest, the initial kinetic energy here, it's equal to 0, and the only energy we have here is gravitational potential energy, it's equal to 4. Now right at the bottom, as we mentioned in the previous example, without friction, the kinetic energy has to be 4 and the gravitational potential energy has to be 0. But since we have frictional force here, the things will be a little bit different. Now let's see what's gonna happen here. the kinetic energy here start to increasing, as we can see here, and the gravitational potential here start to decreasing. But the rate of increasing the kinetic energy, it's not the same as the rate as gravitational potential energy decreasing. So right at the bottom of the ramp here, look at here, the gravitational potential energy, it's equal to, it should be 0 by the way at the end, but the kinetic energy, it's equal to 1 joule. It's not 4 because part of the energy lost because of the frictional force. Back to our example here, we have a ramp. As we can see here, here's the mass m. Now the height here, it's 0.5 meters, and we have frictional force in this one here. Now the forces acting on this object, we have mg, we have the normal force. To solve this one here, work total equal to delta K, the change in kinetic energy. Now work total, we have work done by friction, this one here, and work done by gravitational force. But this one here, we have to analyze it into sine and cosine. This one here, mg sine theta, if this is theta. Now we have work from friction plus we have work from gravity equal to half m the final square minus half m the initial square. Work done by the friction, it's already given, it's minus 5, plus work done from gravity, it's equal to u initial minus u final, equal to, starting from rest, this one here, so the initial velocity, it's equal to 0, so it's equal to half m the final square. So minus 5 here plus u initial, it's mg h, u final here, it's equal to 0 because the height of the object at the final position, it's equal to 0, equal to half m the final square minus 5 plus 3 times 10 times 0.5, this one here, equal to 3 over 2 the final square. Other words, minus 5 plus 15 equal to 3 over 2 the square final, and the final in this case it's equal to 2.54 meter per second. Now let's define conservation of energy. Now based on the previous examples, we found that work total equal to delta K. If the forces we have on the system is only conservative forces, this means the potential energy U initial minus U final equal to half m V final square minus half m the initial square. You rearrange this one here, you will get half m the final square plus U final equal to half m V initial square plus U initial. Now K plus U, this is K by the way, K initial, and this K final. K plus U equal to E, and E in this case is the mechanical energy. In simple words, the mechanical energy is conserved before is the final equal to E initial. The mechanical energy here is conserved in the initial position. It's equal to the mechanical energy in the final position. And remember, we can use this equation only if the forces in the system is conservative forces. Only when the forces on the system is conserved. But if we have other than conserved forces like frictional forces or external forces, in this case here, let's see the work total equal to delta K. In simple words, we use this equation here if we have conservative forces. If we are external forces or frictional forces, we use this main rule. So this is the general case here, and this is special case in this one here. Now look at this model. In this model here, the only force we have here is gravitational force. Starting from this position here, let's see what's going to happen here. The kinetic energy here it's equal to 0, and the potential energy it's equal to 1 joule. Now let's start this one here. Since gravitational force is conserved, as we can see here, the kinetic energy start to increasing and at the bottom here and decreasing at the case in this here and in this one here. Now the gravitational potential energy will be maximum at this position and will be maximum at this position as well. Now the maximum kinetic energy will be right at the bottom in this one here. In all cases, as we can see here, the energy, look at the graph here, the gravitational potential energy starts from 0, and the kinetic energy starts from the maximum value. What I'm trying to say here, energy is conserved. Energy at this position here, let's name this one here, it has to be energy at this position here, and its energy equal to at this position here. Energy in this case, in this one here, it's equal to 1.06 joule. Now at this position here, it's equal to 1.06, and at this position it's 1.06. Now at this position it's only gravitational potential energy. Now at this position here it's kinetic energy. At this position here it's gravitational potential energy. Anywhere in the track here, the mechanical energy equal to 1.06. So at this position here we have potential energy and kinetic energy. So we have here U plus K. In total it's equal to 1.06. Let's have an example. An object of mass m equal to 5 kg placed on horizontal frictionless surface attached to a massless spring with spring constant equal to 500 Newton per meter. The object initially at equilibrium. If a horizontal 15 Newton force is applied to the object, calculate the speed of the object when it's 0.1 meter from its equilibrium position. This spring initially in equilibrium position, this one here. So this one here x equal to 0. now we applied horizontal force equal to 50 newtons, this one here. We need to calculate the speed of this object here when it's 0.1 from its equilibrium position. Now let's just write the work energy theorem. So work total equal to delta K. Now we have here work from external force plus work from spring equal to half the final square minus half the initial square. Now work done from external force, it's F dot delta X plus work from spring, it's equal to half Kx initial square minus half Kx final square equal to half the final square. And remember, it's initially at rest, so this one here equal to 0. F in this case, it's equal to 50 newtons times the displacement, it's 0.1 here, plus, now the spring initially is at equilibrium, so this one here equal to 0. Now instead of plus, we should have here minus half, and K in this case equal to 500 Newton per meter, and X final, this is the final position here, this is the final position here, it's 0.1 square equal to half 5 v final square. You simplify the equation, v final square equal to square root of 1, or it's equal to 1 meter per second. In the figure, an object of mass m is placed on a light spring of force constant K in a vertical position, like in this one here. If the object is compressed by a distance d, this one here, d in this case here, and then released from rest, find the maximum height the object can reach with respect to the point of release in terms of m, d, and k, and consider there's no friction whatsoever. Now to solve this one here, let's just again use the work energy theorem. Work total equal to delta K. Now the question is no friction in this case and no external force, so we can use E final equal to E initial. Again, this one here is a special case from this one here. At this final position here, Y final here is the maximum, and velocity here, V final equal to 0. Now at this final position we have only gravitational potential energy, it's mgy final. Now at this initial position right here, the gravitational potential, if we assuming that this is the reference point and this equal to 0, now we have at this initial position we have elastic potential energy half kx initial square, and again it's at rest, no kinetic energy at this position as well. Now in this one here, if we simplify this one here, we will get y maximum equal to 1 over 2 mg k d square in such a way d here equal to x, the spring displacement. The spring displacement. Example: a simple pendulum of mass 2 kilograms and length 1 meter is released from rest when the height of the mass 0.5 meters with respect to the lowest point. What is the speed of the mass at the lowest point, assuming no friction? To solve this one, let's just have quick diagram here. So we have simple pendulum, this one here, the mass here m equal to 2 kilograms, and the length of this rope here L equal to 1 meters. The height for this mass here with respect to the ground, assuming that this is the ground here, equal to 0.5 meters. Now, what is the speed of this object at the lowest point? So this is the lowest point here. Now, since there is no friction in this case here, so work total equal to delta K. No friction and no external force, and in this case here we can say that E final equal to E initial. The mechanical energy, the total mechanical energy at this position here equal to the total mechanical energy at this position here. Now at this position, let's name it 1 here, and this is 2. Now the mechanical energy here, we only have potential in energy, gravitational potential energy. So the initial position here, it's equal to mgh. Now at this position here, we only have kinetic energy, so it's equal to half mv final square. Remember, at this position here, no kinetic energy because the object here starts from rest, and at this position here, no gravitational potential energy because the height here from the reference point, it's equal to 0. So you simplify this one here, you will get mass with mass here, so V equal to square root of 2gh. And remember, h in this case here is the initial height of the object, which equal to 0.5. So V in this case equal to square root of 2 times 10 times 0.5, or V final here equal to 3.16 meter per second. In the same example here, find the tension at the lowest point. Now at the lowest point here, we have the situation here, and at the lowest point here, we have two forces. Weight is directed this way here, and tension, it's this one here. Now, sum of all forces equal to ma. Now, the acceleration in this case here is the radial acceleration. So, sum of all forces equal to mv square over r. R here, the radius of the circular path, which is in this case here is the length of the rope. Now, sum of all forces, it's tension minus mg equal to mv square over r, and v, we just calculated v from this part, this one here. You just substitute numbers here and you can find the tension in this case. Remember, the mass equal to 2 kilograms and r equal to 1 meters, v equal to 3.16 meter per seconds. Example: a 40 kilogram object is dropped from a height 50 meters above the floor. The object experiences constant frictional force of 100 Newton. Find the speed of the object just before it strikes the ground. Now we dropped an object, this one here, and this is the ground here. The mass for this one here, it's 40 kilogram, and the height, this one here, the height, the total height here, equal to 50 meters. We need to calculate the speed of the object just before it strikes the ground at this position here, and there is a friction in this case. Okay, so work total here equal to delta K. Now, since we have friction, we cannot use E final equal to E initial. This one here, we can't use this one here because there is a friction in this situation. So work total is the work from friction plus work from gravitational potential energy, which equal to delta K half v final square minus half v initial square. Since the object is dropped from rest, so this one will be 0. Work from friction, now the displacement here it's 50 and the friction is going up, so it's minus 100 newtons times 50 meters plus U initial minus U final equal to half v final square. Now U final here, the height of the object when it strikes the ground equal to 0, and U initial here equal to mgh, so minus 5,000 plus m, in this case it's equal to 40 times 10 times the height is 50 equal to half 40 v final square. You substitute numbers, you will get v final equal to 27 meter per second. One more case example. In this situation here, the coefficient of kinetic friction is 0.2. M1, this one here, equal to 4 kilograms and M2 equal to 6 kilograms. If the system starts from rest, what is the speed of M1 here when M2 has fallen in distance 2 meters? So if M2 here fall to 2 meters. Now to solve this one here, work total equal to delta K. Since there is a frictional force in this case here, we cannot use E initial equal to E final. We should use this rule here. So work total here equal to work done by frictional force plus work done by gravity equal to half v final square minus half v initial square. Or we can say that E final equal to E initial plus work done by the friction. So this is y initial 2, and this is y initial 1, and this is y final 2. So E initial equal to M1 G Y 1 initial plus M2 G Y 2 initial plus half M1 V1 initial square plus half M2 V2 initial square. And remember, the whole system it's at rest, so no velocity here. Again, for the other system it's equal to 0, and the initial position it's equal to 0, this one here, and this one 0 for this case as well. So E final here equal to M1G Y initial final plus M2G Y2 final plus half M1 V1 final square plus half M2 V2 final square. And the only one cancel out is this part here, because the final position for M1 is the same as the initial position for M1, which equal to, in this case, equal to 0. Now, since M1 is moving horizontally, then Y1 final equal to Y1 initial, which equal to 0, and the system start from rest, V2 initial equal to V1 initial, which equal to 0, and V2 final equal to V1 final, and let's just name it V final. And Fk here, the frictional force equal to mu k n, which equal to mu k m1 g. You substitute things in the equation above, you will get in this one here V final equal to 4.51 meter per seconds. Now let's define power. Power is defined as the rate at which work is done. In other words, if a force F does a work on an object in a time interval delta t, then the average power delivered to the object is defined as power here average equal to delta W divided by delta T. If F is constant, then power here equal to F dot delta R over delta T, and remember delta R over delta T it's V, so you simplify it into F dot V. Example, an object of mass m equal to 2 kilograms is sliding down in an inclined surface that has 30 degrees above the horizontal. So this 30 degrees at a constant speed 3 meters per second. What is the instantaneous power of the friction force? So let's have free body diagram here. We have the weight is directed this way here, mg, and this one here is the normal. After analyzing the weight, you will get mg cosine theta, and this one here mg sine theta. And since we are looking for the instantaneous power of the frictional force, let's find the frictional force. So sum of all forces equal to, in this case here, the object is moving in with constant speed, so sum of all forces equal to 0. So mg sine theta minus fk equal to 0, or in other words, fk here equal to mg sine theta. And in the instantaneous power of the frictional force here equal to fk dot v. Now the angle between the frictional force and the speed is equal to 180 degree. So this is the direction of the frictional force, and this is the object motion direction. So in this case here, theta equal to 180 degree. So P instantaneous equal to Fk, we just calculate this one here, mg sine theta v cosine 180. In other words, the power or the instantaneous power of the frictional force equal to minus 29.4 watt. And that's it. Thank you for watching.